Hello, everyone. I'm Zhang from USS Lab, Zhejiang University. Actually, I'm not the author of this paper. I present this work on behalf of my colleagues. They cannot come here due to the visa problem. So I'm going to introduce this work on the backdoor attack against vertical split learning. This work is done by USS Lab and Ant Group in cooperation. Federated learning is a widely used machine learning framework for multiple clients to train a model together without disclosing their private data. For example, multiple smartphone users can train a keyboard behavior prediction model with Google Federated Learning Service. Federated learning can be divided into two types, horizontal and vertical. In horizontal federated learning, every client has full feature factors, but their samples are different. In vertical federated learning, clients have the same samples, but each client has only partial feature vectors of the same samples, and the label information is controlled by the server. Backdoor attack aims to train a backdoor model that behaves normally on clean inputs, but misclassifies inputs with a trigger into a target label. In this way, the model will be controlled by the attacker. The backdoor attack on horizontal federated learning is thoroughly researched in recent years. In contrast, the backdoor attack on vertical federated learning is still a blank because the attack setting and data distribution are challenging. In this work, we propose the first backdoor attack on the most popular vertical federated learning scheme, vertical split learning. Vertical split learning splits the global model into different parts and assigns each part to a client. The clients and the server only exchange the embedding and the gradient to keep their data local and private. The training process is as follows. The clients first calculate the embedding vector by the local embedding model, and all clients send their embedding vectors to the server. Then the server aggregates the embedding vectors from all clients with a certain aggregation function. The server leverages the embedding and the label to get the gradient and train the classifier. Finally, the server sends back the gradient, and each client uses the gradient to update its embedding model. In the prediction phase, the input is also held separately by the clients, and each client sends the embedding to the server, and the server derives the final prediction result. In our threat model, we assume that a malicious client, the attacker, wants to poison the server model during training. Specifically, the local embedding model is controlled totally by the attacker, but the attacker can only upload the poisoned embedding vectors to the server and get the gradient back. The goal of the attacker is to manipulate the prediction with a trigger embedding in the inference phase. For example, the attacker sends an embedding with the trigger, and the server will misclassify the dog image into the target label plain, as shown in the slide. So the first challenge we face is a lack of label information. In a typical backdoor attack, the attacker needs to manipulate the samples of the target label, so the attacker has to infer the labels first. We assume that the attacker has one sample of the target label and use the sample to infer the labels of other samples, which we call the fish hook. Actually, this assumption is very limited compared with the existing work. Second, the attacker has no access to the server model, so it's difficult to optimize the trigger to improve the attack performance. Our proposed attack framework, Villain, consists of two modules, that is, label inference and data poisoning. The label inference module is used to infer the label of training samples so that the attacker is able to carry out backdoor attacks with the label information. In the data poisoning module, we carefully design the poisoned data to inject the backdoor into the global model. Our label inference algorithm consists of three parts. The core of the method is to infer label information by swapping embedding. The intuition is to make full use of the shared gradient. For example, if the true label is plain, and we proactively swap the embedding into the plain embedding, another plain embedding, when the model is well trained, then the loss and the gradient will be small. Otherwise, if the true label is dog, different from the swapping sample plane, the loss will be salient and the gradient will be relatively large. So we compare the gradient before swapping and the gradient after swapping. The changing ratio and the absolute value of the gradient are the indicators denoting whether the sample has the same label as the fixed hooks. For better accuracy and efficiency of embedding swapping, we perform pre-selection on the candidate samples for embedding swapping using a semi-supervised binary classifier. To avoid a never-changed embedding swapping pattern, which may be noticed and alarmed by the server, we adaptively adjust the embedding for swapping using the previous inferred data. With the label information, the attacker needs to poison target label samples to inject the backdoor. To realize effective and stealthy backdoor injection, we developed 3 strategies, that is, trigger fabrication, backdoor augmentation, and learning rate adjustment. In trigger fabrication, we optimize the position and the size of an additive trigger to poison the embedding vector. Backdoor augmentation and learning rate adjustment are used to improve the backdoor influence. For more design details, please refer to our paper. We use 4 image datasets and 2 financial tabular datasets to validate the effectiveness of villain. Our experiments are divided into 3 parts. We test the overall performance, we test villain under different hyperparameters, and we evaluate the attack against different defense methods. For overall performance, we test our algorithm with three baselines. As shown in this table, villain achieves the highest precision and the highest attack success rates on each dataset. We validate that the trigger of villain can be added not only in the embedding domain, but also in the data domain. The results show that the data domain trigger is also effective with an attack success rate higher than 98%. We also evaluate villain on different embedding aggregation methods. As shown in this table, villain performs well on different aggregation methods of vertical split learning. For the impact of hyperparameters, we take the server model structure as an example here. We evaluate the impact of server model structure on the attack performance, considering that in real-world scenarios, the attacker has no knowledge of the server model. The results show that a villain is robust and effective on different server model structures. We also validate the label inference and backdoor attack against several defense methods. Existing defenses cannot reduce attack success rate while keeping high clean data accuracy, which means that villain can resist existing defense methods. In conclusion, we make the first attempt to conduct backdoor attack on vertical split learning. Second, we have developed a novel label inference algorithm to locate samples of the target label with only one known sample. Extensive experiments have validated the effectiveness and robustness of villain. That's all. Thanks for listening. Please feel free to contact the authors via email or Slack. The author is online and ready for questions. Thanks.